Hello! So, in this video we're going to go over some definitions and their implications for proofs. In particular, these definitions are on the ideas of the absolute convergence, conditional convergence, alternating series, stuff like that, as we can see. Alright, so the first thing, the first definition that we're going to mention here is what it means to converge absolutely. So, a series, AN, is said to converge absolutely if the series with the absolute value of the ANs converges. So notice where these absolute values are, right? I'm not saying the absolute value of the series, I'm saying the absolute value of the terms. So this idea is that you could have series, and this gets into how the next ones are going to work, but you can have series where some terms are positive, some terms are negative, and they're somehow sort of canceling each other out enough that it stays small and you get something that converges. Life is good. But you can also have a situation, so if you have that situation, say, and you take the absolute value of these things, then all of a sudden you're adding only positive terms. They're all working in the same direction, the positive direction, and you can get something that sort of diverges off to infinity, right? So converging absolutely says that that's not a thing, right? Your thing, even if you sort of take the worst case scenario, make everything positive, you add them up all in the same direction, still is going to converge. In contrast, you can have a series that says to converge conditionally if essentially it's doing what I said earlier, where you have some positive, some negative, and you can have it so that the sort of default, the regular series bit converges, but if you were to sort of undo that balancing act that's happening, right? If you were to take the absolute value of every term, you get something that diverges, okay? I want to point out something very, very clear and very important here that is very often missed, which is that this claim, this is two claims. Meaning that if you were to get a problem, right, and the problem was show the following series converges conditionally, that means you have to do two things, right? You have to do this piece, show that the actual normal series converges, however you need to go about that, but you also need to show that if you take the absolute value, you get something that diverges, right? You have to show both things. Often one of them is easy to show and one of them is harder to show, and I think maybe that's why a lot of the cases students will show the harder one and ignore the easier one, and then they lose, you know, half the credit on their problem or whatever, because it is required that you show both of these things to be true, right? It has to converge on its own, has to diverge if you take the absolute value. Two things. All right. So in the spirit of sort of balancing act in these things is this idea of an alternating series. So if you take some sequence AN of here non-negative real numbers, right? So they're positive or zero things. Then putting a -1 to the n in front, or -1 to the n plus 1, this gives you an alternating series. And again, I want to draw your attention to the fact that an alternating series doesn't just mean that some are positive and some are negative. It has to alternate consistently, all right? So every term has to be the opposite sign of the previous term. So for example, the series, let's go with n equals 0 to infinity of sine of n is not an alternating series. Because although this does change sign, it doesn't change sign every term. It's not consistent. Sometimes it'll change every term for a few terms in a row. Sometimes it'll have the same sign more than once in a row, right? It's not consistently always changing sign each term, and so it's not an alternating series. And we have to be a little careful when we say always changing sign each term, because 0 is signless, right? So you could have a series that looks like, say, you know, -1, 2, -3, 0, -5, right? And this would count because 0 you could think of as a positive. So it would be negative, positive, negative, positive, negative. Likewise, you could have something that looks like -1, 2, 0, 4, -3, right? Which isn't enough to really do a ... But the point is here, I could think of this 0 as being negative, and I could have negative, positive, negative, positive, negative. right? So when I say switch signs, what I really mean is that it can be sort of assigned that -1 to the n, and it still works, because the -1 to the n is killed off by the 0, which is the a to the n term, okay? But I can't have something like 2, 1, 4, right? Because that middle thing has to be negative or 0. Last but not least, I'm drawing attention to this because this is actually a very, very, very standard thing to do in mathematics, and the book that we're using, at least at the time that I'm recording this, sort of goes in a, let's say, atypical direction with their notation. And in fairness to the author, he's very explicit about it. He draws attention, he says, note in other texts, it's often defined this other way, which is what I've written here. Make sure you and the author says make sure you see the difference between the way the authors defined it versus the way that is sometimes defined. That being said, there's a good reason to define this way. So getting into it then, an is a sequence of real numbers. We can make this an plus, which is basically an for all the non-negative an's and 0 anywhere there is an an. And an minus is minus an. This is the way I'm doing it. The author has just an here. So it's negative an for an negative and 0 wherever it's not negative, right? So if you had something like, let's say one of these, right? The an plus would have 0, 2, 0, 0, 0, etc. because wherever it's negative gets a 0, wherever it's 0 gets a 0, wherever it's positive gets the value. Whereas that same string for the an minus, we take wherever it's negative, it would take the negative of that. So you get a positive sequence still. So you're getting sort of the positive version of the negatives, and 0 wherever it's positive or 0. Now this may seem counterintuitive, right? Because it seems like you should just take the values as they are. But there's actually a good reason to do this. And the reason why is that if you remember a lot of the things that we have done throughout the process of proving theorems talk about like, what if, we want the series, or the sequence rather, to be positive eventually, right? By defining it as negative an, I have something that is positive eventually, whereas I may not ever have it if I did just an. And so I could determine something about an plus and an minus, and then do this idea of an plus minus an minus, and this is the original sequence. Meaning that I can use the fact that I have two positive sequences, do stuff, all the hard work on positive sequences for which I have a bunch of theorems, and then use the fact that, say, two convergent sequences, the sum of them is convergent, right? And do this difference to get back to the original. And this kind of thing is used a lot. It's used in function notation, it's used in functional analysis, it's used in any real analysis course past this one. To some extent, we may see it even in the next chapter, in the next part, where we talk about sequence and series of functions as opposed to just values, numbers here. So it is used, what we would call a decomposition is used a lot, and pretty much always is done this way, which is why I'm sort of drawing attention to this, because again, although the author is very explicit about it, and that's his prerogative as the author, it is sort of not made clear in the text that this way, the way the author isn't doing it, is really sort of the standard way to do it, with some notable exceptions, some occurrences where the way the author does it is better, and people usually sort of make those exceptions rather than making that the rule and making these the exceptions, okay? For that reason, in my proofs, I'm going to define these wherever I use them so that it's very clear which way I'm using them. So even though I'm giving you the definition now, I will also give it again anywhere I'm going to use it so that we're all on the same page as to which one I'm using, okay? All right, so that's definitions, implications, or proofs, at least for these ideas of absolute convergence, conditional convergence, and alternating series. And we're done.